folded back on itself in loops, attached to a backing strip, and cemented to the member. Any material stretches or compresses when subjected to a load. An electric current passes through the wire of the gauge, and the change in resistance as the member stretches or contracts is calibrated to indicate the strain of the metal to which it is attached. During testing, the information from the strain gauges was transmitted to a data recorder, which plots the strain or movement in inches versus the percentage of applied load. As an original source tracing device, cameras actuated by inertia switches and operating at a speed of 1/2000th of a second were installed. Shock of a failure trips the switch and actuates the camera in the failure area, in most cases pinpointing the start of the failure. With instrumentation completed and all necessary safety devices provided, the airplane is now ready for the tests, which represent the culmination of 3 years' effort. If a failure occurs before 100% design load, a repair must be made and all existing parts must be revised. Several $1 million worth of engineering and factory effort are at stake. One of the vital tests is high angle of attack, a fully loaded tanker airplane making a sudden maneuver. The test director, located on a stand above the test balcony, is equipped with a microphone to give general announcements to the group witnessing the test or to individual observers stationed at strategic locations around the test airplane. On the balcony below, the pump operators. Each controls the loading of one hydraulic jack under the direction of the pump controller. At the strain gauge, data plotters and deflection indicating machines. Other operators are stationed. 30% design load is called for. The loads must be applied uniformly in increments of 2%. The first visible sign that the airplane is being loaded is that the wingtip has moved upward about a foot. With 30% load on, all data is read. The strain gauge plots are laid out, compared with previously prepared estimates. If everything is going according to plan, the test continues. The director calls for 50% design load, and the wing keeps climbing upward about a foot with each 10% increment. At 100%, the wing has deflected 12 feet. As shown in time-lapse photography, compressing 4 hours of testing into 10 seconds. The load is lowered, and the test is repeated, this time with 1.5 times operating cabin pressure in the fuselage. This particular test is complete. 100% has been reached. The structural changes made as a result of this and other tests provide a guarantee of safety for the KC-135 under the toughest operating conditions. Beyond the ultimate load, what is the strength of the wing? Fulfilling an Air Force requirement for a test to destruction, the critical wing test was repeated, reaching 110% before a failure occurred. Strobe cameras revealed the origin of the break, even though failure appeared to happen simultaneously in both wings. 110% represents the absolute capacity of the wing and demonstrates a growth potential. While the static test was determining the ultimate strength of the KC-135, another test fuselage was slated to undergo hydro-fatigue tests, that is, dynamic simulated flight tests. These tests were designed with the purpose of demonstrating any possible design deficiencies at an early date, to show that the pressurized fuselage has a high level of structural integrity, endurance, and resistance to fatigue damage, and that whatever failures do occur will not impair the safety of the airplane or create conditions jeopardizing safety of crew and passengers. To accomplish these aims, a structurally complete test article was placed in a specially constructed water tank with a capacity of 420,000 gallons. Testing with the fuselage in water reduces cycling time, minimizes damage in case of failure, and provides maximum safety to observers and test personnel. Loads on the airplane were applied by two methods. 8 buoyancy tanks were attached to the floor beams for applying a continuous upload, and 20 hydraulic jacks were provided, 14 for vertical loads, 4 for torsion loads, and 2 for raising counterweights at the beginning and end of cycling. Loads were scheduled to be applied so that one spectrum of loads represented a composite of the expected actual flight experience. Since no service data was available on the KC-135 at the time these tests were conceived, information was extrapolated from a study of KC-97 and C-97 use. A typical test operation follows a standardized procedure. Before each test, a pre-fill check is performed by the test operator, who verifies that all water entry points are open, buoyancy tanks closed, foreign matter eliminated from fuselage and tank area, load cells and strain gauges zeroed, and test equipment operative. Then the tank is closed and the 6-hour filling process begins. After the water level reaches the pressure deck, ground roll load condition is applied. This is the condition simulating the minimum strain to the airplane. Especially trained shop and engineering personnel are used as scuba divers, performing vital functions in preparing the fuselage for testing. The divers also perform minor repairs to the hydraulic system, operate motion picture cameras, close and open valves and doors, and perform inspection between cycles. In several instances during testing, the decision on whether cycling should be stopped has depended on the diver's report on known damage. Divers have also installed remotely actuated cameras for use during cycling at points where high stresses were anticipated. To qualify for the scuba diver program, the personnel are subjected to a rigorous physical examination and a complete training school to prepare them for any emergency. Safety is stressed, with no diver allowed in the tank without the presence of another. The first step in the testing is the application of the ground roll load, which supplies the minimum strain to the airplane for the ground-air-ground cycle. The ground-air-ground cycle represents the maximum and minimum loads experienced by the airplane in typical flight. As the testing continues, the airplane is subjected to cabin pressurization and a series of loads which simulate those loads encountered throughout its flight. A history of loading and stress environment experienced by the airplane during the hydro fatigue test is obtained by the strain gauge instrumentation. This data makes it possible to correlate test findings with predicted results and supplies information which may be used in the design of future airplanes. Cycling is discontinued periodically to permit a thorough inspection of the airplane structure. Prior to draining the tank, the ground roll load condition is placed on the fuselage. When the water level falls below the bottom of the buoyancy tanks, the ground roll load condition is removed. Once the tank is drained, the inspectors begin their task. All damages are recorded, numbered, and photographed. Required repairs are accomplished, and the fuselage is then readied for the next fill operation, and testing is continued. These static and hydro-fatigue tests are but two of the many proof, research, and development tests conducted by the Boeing Airplane Company to assure that their products will continue to be among the leaders in the industry. The tests provide proof of design reliability and furnish basic information which is used to improve current and future designs, providing flight safety through ground tests.